Okay, so the next topic is, well, so that's what we do. How do we actually do it? Well, slide 19 is a crude schematic of the kernel. So the microkernel on the left, the only components I've illustrated here are process creation, messaging, and the scheduler. The box on the right is a kernel module. This is an optional module. It's a .a length file, which if you put in your build directory, when you build your file, it'll get built into the image. And when the image initializes, the APS scheduler in the libmod aps.a file will hook itself into the microkernel. It runs as part of the kernel space, so there's no address swapping between them. And what happens is, process creation and messaging automatically communicate with libmod APS in order to position threads into the correct partition for things like partition inheritance and messaging and partition inheritance and process creation. And the scheduler automatically hooks itself into APS for the key scheduling operations of the clock interrupt handler and things like blocking threads, readying threads, and the critical select thread, which is the decision process of what thread do I run now. What the adapting partitioning scheduler does, and it's hinted over at the right, is it uses a mathematical algorithm. Rather than doing a huge number of if statements, as the previous slides might suggest for all those different possible scenarios as to do you have free time, are you an overload, are you an underload, instead, what I did is I wrote a merit function, and I wrote code to evaluate the merit function, the repartition, and then it chooses the partition with the best merit function value. It turns out that this was the easiest way to define the algorithm for purposes of testing it, and I wrote a simulator in Python. I chose Python because you can write a merit function of this kind of complexity in a single line in Python, and it was very easy to try a very large number of merit functions in a large number of different scenarios to prove that the merit function actually implemented the intended algorithm. So it turns out that's a definition of the scheduling algorithm written in that math, although I used to have a whole slide for that mathematics, but I was hearing snoring from the background, so I shrunk it. What you need to know about the algorithm is this on slide 20. And it's English, so don't be afraid. Partition sees real-time behavior when it's under budget. Really simple. It behaves like a party parental scheduler that you know and love when nobody's using up as much CPU time as they possibly can. When you do use up as much CPU time as possibly can, we get fair share scheduling, which means if you're in a partition with a guaranteed 30% budget, you're guaranteed 30%, and nothing can take it away from you. In the event that you have equal priorities between partitions that have the same share as you or in the same budget state as you, then we interleave the partitions so we minimize the latencies. Free time we can give out by priority or give out by the ratio of budgets. It's actually a configurable option. And there's also critical threads in the event that there are a few interrupt level or a few interrupt handling threads that you want to execute in strict priority mode independent of budget. You have that ability too. All right. So we've been having a lot of fun, but slide 21 asks the most important question. You know, this is pretty fancy, but is it fast? There is no point running a fancy scheduler if it's going to take up all the CPU time, and if you're not actually going to do any work, there's no point thinking about what scheduling algorithm to execute in real time. So, a couple of points about APS's runtime behavior. First thing is scheduling overhead increases with the number of partitions, number of messages per second, number of clock interrupts. This is true for all schedulers. It specifically does not increase with the number of threads. We designed the algorithm very carefully so it would increase the number of threads. So there's no possibility that APS could trigger an avalanche, as I explained in one of the war stories in part 1 of this video. Second of all, a number of operations which are very expensive in other fair share scheduling schedulers is actually very cheap in APS. For example, inheriting a partition as part of the message receive costs nothing, nearly nothing. Joining a thread to a partition is extremely cheap, and dynamically changing partition budgets is very cheap. Message inheritance actually doesn't even require an extra kernel call, basically zero cost. So you might ask, well, what are the computational requirements? If you read the fine print 2 slides ago in the math weenie section, you notice there were actually divides there. But we managed to execute the algorithm without doing any floating point. In fact, we do no division. We don't swap any extra address spaces to run the APS algorithm. We can run that merit function evaluation independently and simultaneously on 2 different CPUs in an SMP system with no messaging communication between them, and the algorithm still does the right thing. The algorithm does not have to keep history of the decisions it made in the past, and it still does the right thing. In fact, the only computational requirements this algorithm requires is it needs to be able to do 32-bit multiplies and 64-bit adds. And the bottom line is the overhead of this algorithm is about 1% of the CPU, which I've been told is pretty good when it comes to fair share schedulers. Slide 23 shows that we've decided to give you lots of ways of controlling the API scheduler. The basic things that you want to do to control the API scheduler is you want to define partitions, and you want to be able to launch applications into partitions. So one simple way of doing that is we provided an extension to the language of the QNX build file. You can define partitions and launch applications to the build file. This is really handy for an embedded system where you want security, so you set up an initial partition configuration, and then you lock it down. You can also set up partitions with the command line using the APS command and the on command for launching applications to partitions. And this is completely dynamic. You can change your mind about where your applications are. You can change the size of your partitions at command time. You can move the partitions around. You can also use the Momentix integrated development environment in release IDE 4, which I believe came out in 2006. You can drag and drop processes into partitions, and you can dynamic configure partitions using a graphic interface for those people who don't like the command line stuff. And finally, for the true hackers amongst us, there's a header file you can embed in which gives you full interface to absolutely everything, which of course would be the true choice for anybody who's willing to wear lab coat. All right, one of our customers who happens to have a lot of military clients said, prove to me that APS is secure. Yes, well, what do you mean? Well, what they were looking for is any possibility that a rogue application could grab more CPU time than some APS configuration would nominally define. And we said, well, no, that can't happen, for the simple reason, shown on slide 24, that AP enforces partition budgets on every single clock interrupt. Okay, well, can you muck with the configuration? Well, yeah, but you can set the security so that root has to do it. Okay, well, supposing you got root, can you muck with it then? Well, not necessarily, because you can also configure APS so that if you launch an untrusted application in a child partition, because partitions have a hierarchy of one partition creates another, the child partition is not allowed to grow itself above the size of the parent. So even if some rogue application got hold of the root password, it still cannot create a sub-partition that would be bigger than the partition you started it in. And finally, the configuration can be locked. So for absolute security, you can set up your partition configuration in your build file, lock it, and then nothing can change it except a new build file. Now, there's an obvious way of circumventing this security, and I'm perfectly happy to say it, is what you do is you mask the clock interrupts, and that'll prevent APS from running. But if you mask the clock interrupts, you've got lots of other problems than some thread using more CPU time than you budgeted. All right, so the last word is, why is this cool? I think fundamentally the reason why adaptive partitioning is cool is that because it's engineerable. Now by engineerable, it means that an engineer at the customer whose responsibility is the behavior of the whole system can define global behavior for the system without having to talk to, say, 100 developers in 100 different departments. As I mentioned in video 1, a problem with large development is lots of applications and designers choosing thread priorities independently without any consistency as to what priority 21 means and whether or not you should have been to priority 20 or priority 22. And there can be large differences in system behavior by making small errors in choosing a priority system. In APS, I think there are 4 reasons why it's engineerable. First of all, we've come up with a very simple means of identifying what a unit of work is. In other words, what belongs in a partition. Very simply, what belongs in a partition is all the children of a designated process. So you don't have to explicitly list 1,000 threads and say they belong in partition A. You just say, well, this is my startup process. Anything it does will belong in partition A. And second of all, we have message inheritance, which means that you don't have to put your file systems, your global utilities, your resource managers, or the operating system into a particular partition, because it'll automatically inherit into the partition of the client, which means in general you do not have to do extra engineering for your service layers. Finally, there's a very simple thing we decided to do, is we decided that we would do global share management. We would define global behavior of the system rather than behavior individual threads, and the language we would use is percentage of CPU time, because we've discovered that the one language that both the sales guys and the engineers can agree upon is a percentage. It's not nanoseconds or milliseconds or megahertz. They're quite comfortable saying, well, we shouldn't spend more than 10% of the CPU on this thing. And even when you change processor power, it's still relatively easy to rebalance the numbers. Finally, if you absolutely need to break the rules because you've got some interrupt latencies that you must meet, there are critical threads. It's an escape clause to get you out of the limitations of a fair share scheduler. And very lastly, It's secure. All the parameters in APS can be set for a variety of security levels, or security can be turned off completely to make it easy to configure and test configurations. That's why it's engineerable, and that's why it's cool.